For my final create project in my AI focus, I decided to work on another computer vision application because I personally believe that computer vision was just the most interesting subset of AI to explore for me. So I decided, why not build a computer vision project as my last create. So today I'm going to be walking through my project on understanding the Amazon from space using multi-label classification and computer vision. So this is more of a technical walkthrough. If you would like to just kind of understand the problem and the value proposition of the Amazon rainforest, you can watch the YouTube video or the article I wrote. And then I'll step through the table of contents. So I'm going to be explaining a bit about the data set so we can understand it better, go into the different computer vision and convolutional neural network architectures that I used for this project. I played around with a bit. I just wanted to see how all of their different performances would compare, just because I've never worked with satellite imagery data before, so I thought it would be interesting to put them to the test. So then we have the Amazon Satellite Machine Learning Classification Model, and this is when I'm visualizing the data, pre-processing it, building the model, and then lastly, I'll just draw up my conclusions and share my final thoughts on the models and just the overall project. So I'm going to be going through about the data set first. So this data set was a competition data set that was contributed to Kaggle by Planet. So Kaggle not constantly, but they host competitions, and often they have partners share data sets for machine learning engineers to just play around with and try to build a model for. So this one was by Planet, and the dataset contains training CSV files and then train/test images of satellite image chips of the Amazon rainforest. And the challenge that Planet proposed was creating a model that was able to label these images based on their atmospheric conditions and land usage. And then the overarching goal of this was to try to track the human carbon footprint on the Amazon rainforest, so we can understand the land usage in the Amazon rainforest better. And then yeah, so the labels were not mutually exclusive, so meaning that one image could have 1, 2, 3, even 9, up to 9 labels, so and more than that. So an image could fall under several classes, and the classes were artisanal mine, conventional mine, partly cloudy, habitation, bare ground, blooming, selective logging, road, cultivation, water, agriculture, haze, primary, blowdown, cloudy, clear, and/or slash burn. And I've also linked the dataset in the article and the video I made, but I'll link it again, and you can find it here in the Kaggle notebook. So, going through the convolutional neural network architectures. So I used VGG16. VGG16 was actually a model that I used for a project earlier in the year on classifying pneumonia in patients. AlexNet, I actually played around with it a bit for a competition, but ended up not really building a complete model with it. So there was that. And Inception v3, I was new to it, so it was really cool and interesting to learn about it. And then the concept of transfer learning. Basically, it's a concept in machine learning where you can actually take knowledge that was learned by one model that was pre-trained on the dataset, and then you can leverage that pre-trained model onto another dataset, and then the benefits of that would be faster training time, better performance, and improved generalization. So that would likely reduce overfitting. Okay, so walking through the Amazon Satellite Machine Learning Classification Model. So I just began with data exploration and data visualization, loaded in all the directories and then the CSV files, took a look at the head of the data frame, and then printed out the shape. Now, in this Kaggle notebook, I actually haven't printed out shown the output, just because Kaggle was running into some memory allocation issues. So that's why you can't see the output in this one, just the code. And then afterwards, just printing out the data from shape. Printing out the data from shape is actually really helpful because then you can find out how many test samples or training samples that you're working with, and then kind of work from there. So you know if you have too little data samples, that you need to find a way to work around that. And then I just use regular expression to go through the labels, and then figure out the distribution of labels. So how many values there are, or how many test samples or training samples there are per number of labels. And then I just wanted to see some examples of the labels with so some examples of the values with 1 label, some examples of values with 6, and some examples of values with 9 labels, just to make sure it's working. And then I use matplotlib, which is a data visualization library, and I just trying to visualize the distribution of the different of the number of values. So again, you can't see the output, but my conclusion from that was that most of the images had either 2 labels, 3 labels, or 4 labels, and they were pretty equal in number 1, 5, and 6 labels, which don't appear too frequently. And then images could be classified under 7, 8, or 9 labels, which rarely appear in the dataset. So it was obvious and evident that there was an imbalance there in terms of distribution of the number of labels. And then prior to opening the dataset, I had looked through the training CSV values and the testing CSV values, but I actually did not really understand what the images would look like. So I used CV2 to visualize all the images to understand exactly what our machine learning model is going to be working with. And then going down to data preprocessing, so importing NumPy and over here and trying to just load in all the images. Again, there were memory allocation issues, so I could not load in the entire data set. But here I'm basically just loading the images, converting it into an array, and then just printing out the shape of my array for my images, and then going through and all the tags and trying to get all the singular tags for all of the single tags for each of the images and the training samples. And then going through and splitting the tests, the test and the training values, and then we begin training the model. So again, I started with the VGG19 architecture, and here I use a sequential API instead of the functional one, just because it made more sense since it was not necessary for the VGG19 architecture to use the functional one. So I imported sequential, conv2d, max pooling 2d, dense, flatten, dropout, max pool 2d, batch normalization, all the layers that you need for this architecture. And then imported the model checkpoint callback. So just built the VGG16 sequential model, and then compiled it and I used the binary cross entropy loss and the atom optimizer, and then I tracked for accuracy. And then I use model checkpoint to monitor the model for the highest accuracy, and then only save the model with the highest accuracy or the best accuracy. And then moving on, after that I tested it on AlexNet. So again, I used the sequential API for AlexNet, built the model, and then worked through it. Again, I had to keep some sort of level of control between the models just to keep it even. So again, I used the binary cross entropy loss, the atom optimizer, and then fit the model to the data and trained it for 25 epochs. And then I used, finally, for the last one, the exception architecture, and in this case, I actually used a functional API. I also combined transfer learning here. So I also, again, same model or same loss as the other models. So binary cross entropy, and then the atom optimizer, and then finally, as the last metric, I use the accuracy metric. And then a performance side note. So originally, I actually trained all of these 3 models in an IDE, so I used PyCharm instead of Kaggle, again, due to memory allocation issues with the notebooks, and the training times were incredibly slow. I was waiting like at least 2 to 3 hours for each epoch to train, which is way too slow. So I also noted the model performances in the Medium article I wrote, but just to reiterate here, so VGG16's training accuracy was 0.93157, and the validation accuracy was 0.9324. And then the training speed was definitely the slowest, but at least there wasn't too much of a difference between the training and the validation accuracy, so that indicated that it was not overfitting. And then we had the AlexNet, the training accuracy of 0.94084. This one had a higher training accuracy than VG16, but if you look at the validation accuracy, it had a validation accuracy of 0.9276. The training speed was in the middle, and yeah, so that was pretty interesting and something to note for sure. That although the training accuracy of AlexNet was higher than VGG19, the validation accuracy was a lot lower. So, and then going through in the last one, Inception V3 with combined with transfer learning. The training accuracy was 0.9472, whereas the validation accuracy was the lowest out of all three of them. It was 0.9073. But this one, the training speed was the fastest. And I will note here that the training speed of Inception V3 was a lot faster than AlexNet and VGG19. So that is something to take into account. And in conclusion, this was actually really such an interesting project to work on, and definitely like looking back on it and reflecting back on it, it definitely kickstarted my passion for environmental issues. Prior to working on this project, I had kind of tried out a bunch of different sectors. So I worked on projects that were in the medical space. I worked on projects that were more so space exploration technologies. And I've got to say that out of all of them, I really enjoyed working on machine learning projects that had data sets related to the environment the most, and I found them just the most interesting. So yeah, this concludes basically my technical analysis of my project. If you would still like to read through or try to gain deeper insight into my work, again, I've also already written an article on it, and I can link the Kaggle notebook, and yeah, that's basically it.